Hi, I'm Prabha, a student of MTech Executive. Uh, I'll walk you through regarding the multimodal learning concept. So this paper is basically focuses on the unlearning pattern, optimizing those patterns. So before I get into the paper, let me give you a little background. So multimodal unlearning is in a very naive state as on today. So we have very few handful methods available and which focuses mainly on the unlearning techniques from the beginning. So let's take an example of the single image unlearning. This aims to erase the visual pattern of the real world entities. So basically, in this case, the model has to train on the and fine tune on the data on specifics which needs to forget. So saying it has to go through the complete process of unlearning. It's a processing overhead from the scratch. Now we have two benchmarks also available today. One we call as a multimodal large language model unlearning. This it uses the fictional profiles and basically it adds up the misalignment and hallucination uh, and then compare with the real world real truth. So this is how it identifies and what to be undone, and it is completely textual based. Uh, and another benchmark we have available is a clear benchmark. So the this is basically it has the long explanatory textual context. Rather, I'll call it as a chain of task, which helps us to generate the images. Mm, and they are completely fictional. So based on those, model learns the forgetting scenarios. So we are basically developing, training the model on chain of thoughts or chain of tasks to enable what to unlearn. So again, this is also one kind of a benchmark, and it is very limited in terms of the scenario because it's not related to the real world data. So that's how this multimodal unlearner comes into the picture. So both the benchmarks, what we learned, and even the single image unlearning, they have a processing overhead. Whether you talk about the fictional images or whether you talk about adding hallucination and then learning from the scratch, it's a overhead. So this paper talks about the multimodal unlearning, and it leverages the existing framework of multimodal unlearning pattern. Just that it adds up a weight saliency to add to the parameters to focus on the specific that needs to be unlearned without impacting the data or the visual context which needs to be captured. So in this case, you will see that it improves the performance and also it focuses on the dataset that needs to be unlearned. Before I get into the details of the algorithm, let me go through first the basic concept used here. The vision encoder. Vision encoder is nothing but the vector uh, for the vision features of an images. So that's a raw image features which is presented as part of the vectors. Projectors. Now this is very interesting to understand because the vision encoder output. This is the feature vector, right? That has a very limited dimensions, basically between 1024 to 4096, right? And when we try to provide this feature vector to any LLMs, we have to make sure that it aligns to the embedding space of the LLM, which is fixed. Basically starts from 4096 to 122288, right? So our vector, the current may or may not align with the embedding space of LLM. So we introduces a projector. The job of this project is to map the output of the vision encoder into the embedding space of the LLM. So the output will give you the feature vector only, but it has wrapped into the in a such a way that it can be mapped to the embedding space of LLM. Now we have the feature vector available. Now we have the questionnaire also available related to the images. When we provide this feature vector along with the projector and the questionnaire to the LLM, there is an expected sequence of tokens as an output. So that is what we call as the output for the LLM. That's a basic concept used here. In this case, what will be the loss here? So imagine that we provide an image and as along with the questionnaire, we get the sequence of tokens as an output. So let's assume I ask a question of what's the color of the tree, and there is an image of the tree. So the expected output or the output the LLM will provide is something like the color of the tree is, just a sec. I'll say the color is green. Right. So imagine in this case, let's say we have the output till the length s minus 1. So we already got the output of the color s from the LLM. So what is the probability uh, of getting the word green when we have all the previous output available? So the expected prediction, the model prediction probability to know the correct token at the position S when you have the tokens available for S minus 1, that is the difference between the prediction and the ground truth. We call it as a loss, right? Considering that we have S minus 1 tokens available. So that's a basic. Now, this loss, let's assume we have two data sets. One is the forget data set, which has all the images, questionnaire, concept, and answers available, which needs to forget. And we have the data set available for that information or the image that needs to be retained. So in this case, the total loss or the joint loss is to maximize the loss which needs to be forget and minimize the loss which need to retain. So since consider that we are maximizing the one loss and minimizing the one loss, so both of the are going into a different direction tangentially, right? So that may create a problem because when we try to optimize this joint loss, since this both the loss are in a different direction, it may tend to create a problem. So that is where we have uh, uh, something comes as a mask. What is the mask here? Salient mask is basically the parameter or the base which will target specific parameters, which will enable to maximize the loss for the forgetted image context, and it will not impact the the information or the context, visual context to be retained. That's the job of this mask, Boolean mask. Now comes back to the question is how to calculate this gradient mask, how we know what is the value. So in this paper, we have used the Fisher information matrix. Basically, that depends on what is your targeted data set and what is your preserved data set. Based on that, what is the delta in between these two? That's how this gradient mask is calculated. So in this uh, paper, what is the target data set? Target, because the target is to forget or unlearn the visual context, the visual context of and not the textual context. So in this case, you see we have the visual context, the respective questionnaire, and the concept which needs to be forgotten. That is your target data set. What is to be preserved? We have to preserve the image which needs to be retained. That is your image data set, their questionnaire, and the question. along with the textual information of questionnaire to be retained, textual information of the questionnaire that needs to be forget both. So we are retaining the textual information of the complete data set, which is your forget and retain, and also the image context of the data which needs to be retained. Only part which we are forgetting, we are forcing the model to unlearn is the image context, the visual context of this data set. So in this case, we know what is the target and what will be preserved. So we can find out the gradient mask. Gradient mask is the relative ratio between what to be targeted and what is your preserving. Which is since we are masking them as in one, so it'll give you this gradient will always keep you within the probability limit. That is the whole concept in this paper. So focusing on how to optimize this gradient mask so that we can force the model to unlearn the specific visual context without impacting the data set which needs to be retained. And this has been run in both your multi-model unlearn and as well as the clear, both of the data set it has run, and it has shown the results. Now coming back to the opportunity, after going through this the complete paper, although it's a good optimization result shown, but keeping the scope in the picture, we do have opportunity focused on this paper. Three major points which I can figure it out, which has an opportunity to explore more. One of them is that the gradient mask application on the benchmarks. This paper is focused only on the multimodal unlearning, large language unlearning, and the clear data set benchmarks to apply this gradient mask. So because these are the two available right now, this can be explored more for the other benchmarks available in the market. Second thing is it focuses only on the Fisher information matrix to calculate how the gradient marks should work, right? How to optimize this on this matrix. As part of this algorithm, we do have many available. You'd call it a Hessian matrix, you call it a Newton matrix, you have KL divergence also. That can also be explored to find out whether we can have a better gradient mask can be calculated. Third one, which is very important, maybe a little out of the box, but since we are applying the unlearning on a visual context in the LLMs, we can explore to as a replacement of the visual context. So here we are focusing that these are the data sets to be unlearned, right? We can also focus on replacing that visual context. So replacing a visual context in terms of, let's say, replacing a flower with another flower, replacing a face with another face instead of unlearning it. So that is also a new opportunity to learn, and there are many more, but these are three very important and main related to the paper which I can find out that can be explored as a new paper. So thank you so much. It's a good learning. It's a new domain to be explored, not much information and not much methods, process available in the industry, but I can see there are many in process explored, available to be explored. So yes, we can work it out more on this. Thank you so much. Thank you.